This is the last lecture on production economics, the third one. We're going to start by looking at a production function as a function of a number of inputs, x1 to xn, subject to a standard constraint, which is a cost constraint. In that case, we get this Lagrangian function. We take the first order conditions where the partial of the Lagrangian with respect to any xi is the marginal product. Remember, marginal product is the first derivative of the production function with respect to xi minus r lambda times the input price of xi. And we set that equal to 0. We do this for a number of different inputs, and we get this standard result that the ratio of the marginal products is equal to the ratio of the prices. We also have this condition here, which basically brings back the constraint. Now, the second order conditions are of interest because we construct this bordered Hessian matrix as follows. These are the first and second derivatives of the Lagrangian, so L11, L12, all the way over to L1n, and then we border the Hessian with the input prices, the negative of the input prices at this point, and this 0 down here. Now, this bordered Hessian matrix has to be negative definite if we're going to have a maximum. So how do we know whether or not it's negative definite? Well, we take the principal minors and the determinants of those, and they have to alternate in sign. So the first one has to be greater than 0 in this case, and the second one less than 0, and then they alternate further on. Now, in this problem, we can take the Lij, which refers to the second partial of the Lagrangian with respect to inputs xi and xj. Well, that's the same as taking the partials of the second partial of the production function up here with respect to xi and then xj. And the reason for that is, you'll see if you try to take two derivatives here, you end up with 0 in that point. So now the principal minors must alternate in sign, as I mentioned, for that maximum. And what's interesting is we can construct what's called the expansion path, and along that expansion path, we find that the value of the marginal product of I divided by the input price of I is equal to the value of the marginal product of j divided by the input price of j. And how do we get there? Well, here we're assuming just an x1 and an x2 instead of an I and a j. And what we do is we take the first order condition where we get f1 over r1 equal f2 over r2. We multiply both of these by p. So we multiply both sides by p, and we get this result here, that the price times the marginal product of 1 divided by the input price of 1 equals the price times the marginal product of 2 divided by the input price of 2. That gives us this result where the value of the marginal product of I is equal to price times marginal product, and then we get this result, which is the formula for this expansion path. Now notice here that if we take this budget constraint and we run it parallel, then it is tangent to this isoquant at this point, and if we make it parallel up here, it'd be tangent here. All along that expansion path, we have these tangencies between the cost and the isoquant. And then x1 star and x2 star are our optimums. Now we look at the dual problem, which is a minimization problem, where the cost, we want to minimize the cost, which is given by the sum of the input prices times the amount of input used, subject to a particular level of output, which we've denoted Q superscript 0. Set up the Lagrangian the same way, but this time we have the objective function is the sum of Ri xi. We use this as our Lagrangian multiplier, this theta, and we then have Q0 minus the production function. Taking first derivatives of that, the first order conditions, we get that theta is R1 over F1, R2 over F2, which is exactly the opposite of what we had with lambda. All right, with lambda we had F1 over R1, F2 over R2. Now we've got theta, and we've got R1 over F1, R2 over F2. So we invert both sides, and then we get 1 over theta is equal to the marginal product of 1 over the input price of 1 equal the marginal product 2 over the input price 2. Multiply the tops here, the marginal products, by P, the output price, and we get value the marginal product of 1 divided by R1, input price R1, is equal to the value the marginal product of 2 divided by R2. And notice that we get this result here where theta is 1 over lambda. And that's important to keep in mind. Again, the second order conditions require that the bordered Hessian is now positive definite, so that all the principal minors, the determinants, are greater than 0. Now, returning here quickly, we find that this lambda is the shadow price, or the addition to output if an additional dollar of budget is available. So it asks how much more can we produce if we increase our budget by $1. Theta, the other Lagrange multiplier, is then interpreted as the addition to cost from producing an additional unit of output. And again, theta is equal to 1 over lambda. So then the third possibility is that we have unconstrained profit maximization. And in this case, we set it up as price times production minus RIXI, the sum of that. And we get these first order conditions, which again lead us to the price times the marginal product, which is our value of marginal product, is equal to the input price RI. Second order condition requires that the second partial of the profit function with respect to any input squared is less than 0 for all inputs. And we get that the price times the first derivative of the marginal product of I with respect to xi has to be less than 0. So that's the price times the second partial of the production function with respect to xi has to be less than 0. That implies that P times F sub II is less than 0, and that implies, because price is positive, that FII is less than 0, which indicates that we have diminishing marginal productivity. Now, the second order condition for profit maximization is that these principal minors alternate in sign. So pi 1, 1 is less than 0. Then the next principal minor, the determinant, is greater than 0. Then the third one is less than 0, and so on, alternating in sign. For an unconstrained minimization problem, suppose we had an unconstrained minimization problem, all the principal minors would be positive. So constrained versus unconstrained optimization does, however, present an interesting comparison that has an economic interpretation. So let's look at this diagram here, where we have this expansion path. And along the expansion path, we use our mathematics to find that X star is the optimal unconstrained maximum. C star, however, is based on a constrained optimization problem, and in this case, the optimum is C star. So then the question is, and again, the equation of the expansion path is given in this blue box, and the question is, what happens if we put a constraint on one of the inputs? Suppose you're originally at X star, but now X1 is constrained to be X1 bar instead of X1 star, where X1 star would be to the right of X1 bar. So one does not go to A if there's a constraint. In other words, they don't go back to this same isoquant, but rather they have to go down to B on the expansion path. So rather than going from X star to A by using more of input X2, rather you, for an optimum, drop down to B. So that's the constrained optimization problem. Now we're going to look at the interpretation of that a little later on. In fact, right about now. For the unconstrained optimization, we get that price times marginal product of I is equal to R of I. We can rewrite that by going 1 over P is Fi over Ri, which implies that 1 is equal to P times Fi over Ri. So in an equilibrium, we would have an unconstrained equilibrium would result in this particular set of conditions or condition. All right. So we find for constrained optimization, however, that this result holds. And notice the main difference between the two. That main difference relates to this equal to 1 component. So given this, we can look at a particular problem. Let's look at a particular problem here. Let's assume that Exton Auto Corp receives a 10% subsidy, maybe due to COVID. But labor bargains for a 15% wage increase. What happens to the amounts of labor and capital that Exton Corporation is going to employ? Well, we need some assumptions, and these assumptions are going to be followed a little later on as well. First, we assume that the firm operates in stage 2 of production. That implies that it's the partial derivative of the marginal product with respect to any X input that's less than 0. So that means that the second partial derivative of the production function with respect to Xi would be less than 0, whereas the first derivative, the marginal product itself, is greater than 0. Number 2 is that second order conditions are satisfied. And number 3 is that the cross partial derivatives of that production function, so the partial of any given marginal product I with respect to some other input xj, it has to equal 0. So that's a key assumption, that if I change the amount of labor I use, it doesn't affect the marginal productivity of capital. So to begin with, we have this condition that the value of the marginal product of K divided by the input price of capital, which we denote R here as rental, is equal to the value of the marginal product of labor divided by the wage rate, and it's equal to 1. Now, what happens with our conditions? Well, for capital, we find that the price has gone up, which is by 10%. Which means we multiply the value of the marginal product of K by 1.1, but the input price is not changed, and of course the company is unable to change that R. All right, that's an assumption of perfect competition, that you cannot change the input price for any of the inputs. So what do they do if the marginal product of capital times this 1.1 divided by R now exceeds 1? Well, you have to reduce the marginal product of capital by hiring more capital. So that's the only way you're going to reduce the marginal product. That's the only thing that you can change as an agent, because all you can do is hire a different amount of capital. You cannot change the prices. So for labor, we get a slightly different situation, because now the price has gone up for the commodity, but the wage rate has gone up by 15%. So it's gone up by more than the price has gone up, which is 10%. So this is less than 1. So to increase the marginal product of labor, one hires less labor. Consider another example. Suppose you got a 50-50 crop share arrangement in return for the use of land. This effectively reduces the price of the output to the tenant by 1/2. So the tenant has a lower price now, what should the owner do to get the tenant to use the optimally desired amount of fertilizer from the landowner's perspective? Well, we look at this diagram and we see that the value of the marginal product to the owner is given by this line here, but because the tenant gets half of the output, that effectively means the tenant gets half of the price. So that value, the marginal product of the tenant is half of what it is for the owner, and that line is represented here. So the tenant wants to go and produce or use this amount of fertilizer, whereas the owner would like the tenant to use more fertilizer. So then the landowner would have to subsidize the tenant by this difference in order to be able to get the tenant to produce or use the amount of fertilizer that the landowner would desire. All right, let's look at one other situation here, and that is a case of multiple goods and multiple inputs. In this case, we have profit is equal to the sum of the PI QIs, where there's M goods, minus the sum of the input prices times the amount of the inputs used, and there are N inputs. Now we have to, in addition, bring in this production function as a constraint, because it tells us what the relationship is among the various Q's and the X's. So we form this Lagrangian where we put in the objective function as before, and we have lambda, the Lagrange multiplier, times the constraint. So we first take the Lagrangian and we differentiate the Lagrangian with respect to one of the outputs, Qi, and we get this result Pi minus lambda times the marginal product of Qi. Well, that doesn't make any sense. It's not the marginal product, it's just the partial of f with respect to Qi. And we set that equal to 0. With regard to any input, say xj, we take the partial of L with respect to xj. We get this minus rj minus lambda, and now we have that marginal product of xj equal to 0. And finally, we get our constraint back when we take the partial of the Lagrangian with respect to lambda. Now, we can look at an output-output relationship by looking at any two equations in one. So we look at this set of equations 1, and we find that we get these results P1 minus lambda times partial of f with respect to Q1 is equal to 0. We do the same thing for P2, and we then solve for lambda, and we find that P1 over the partial of f with respect to Q1 is equal to P2 over the partial of f with respect to Q2. Rearranging this and ignoring the lambda, in other words, we're just looking at this component here, we get that the partial of f with respect to Q1 divided by the partial of f with respect to Q2 is equal to minus the derivative, the total derivative Q2 over Q1, derivative of Q1, and that is the marginal rate of transformation, which is the slope along any production possibility frontier. So this relationship here refers to the production possibility frontier. We also know that the prices, the marginal rate of transformation, is equal to the price ratio P1 over P2. So we can also look at two equations in result 2 here, and that basically gives us something similar to what we had done with one input or one output and two inputs. So for any two equations in 2, we get that minus lambda is equal to the input price divided by the marginal product of that input, and that's equal to the input price divided by the marginal product of another input, and rearranging, we get that the ratio of the input prices is equal to the ratio of the marginal products, which is equal to the marginal rate of technical substitution along an isoquant. Now, the more interesting case is the input-output case, because we can take any equation in 1 here and any equation in 2, and we then look at what happens. So the first result is that we get minus Rj divided by the marginal product of J equal to the output price divided by the partial of F with respect to that particular output. And that's equal to this lambda over here. Now, ignoring the lambda and just setting these two together equal to each other, we get that the input price of J divided by the output price of I is equal to the minus of the partial of the production function with respect to input xj divided by the partial of the production function with respect to output qi. So we refer, and that of course is equal to the partial of qi with respect to xj, input j. So we write that as the input price is equal to the input price of j is equal to the price of output I times j, the marginal product of xj, in the production of qi. So we refer to that as the value of the marginal product of j in I. All right, so let me reiterate that. We have this relationship here, and what it tells us is that the input price of input j has to equal the output price of good I times the marginal product of j in I. So the marginal product of input j in the production of output I, and that's we denote as the value of the marginal product of j in I. Now, what that implies is that the marginal rate of substitution of ij, so I for j, is equal to the marginal rate of transformation I in j. So this diagram here is a bit more complicated. So what we have here is two outputs, and we have a production possibility frontier. We have this condition here that the production possibility frontier is tangent to this price ratio. And at that price ratio, we construct what is called an Edgeworth-Bowley box, where we trade along here, and we have individuals now represented by indifference curves trading along that price line here and dividing the outputs given by this point here, dividing that amongst each other. So amongst the two people or the two players in the who are the two consumers. Now notice that the marginal rate of technical substitution is not equal to the marginal rate of transformation. So Rj is equal to Pi partial of Qi with respect to Qj. So we write that again as the input price of j is equal to output price of I times the marginal product of j in I. And the same thing here. This is the second condition for different inputs and a different output. We set these up so that we get this result here. So we get that the ratio of the input prices is equal to the ratio of the output prices. So input Rj, input j is used in the production of I, input k is used in the production of S, so we get that price ratio, and then we multiply it by the marginal product of j in I divided by marginal product of k in S. So that implies that the marginal rate of technical substitution j into k is equal to the marginal rate of technical substitution of I in S times the marginal product of j in I divided by the marginal product of K in S. An application, we find that the value of the marginal product of input I in the production of J divided by its input price is equal to the value of the marginal product of input K in the production of good I divided by the input price of K, and that has to equal 1. So this is very similar to what we had previously in the example we looked at. So let's assume that a farmer produces wheat and barley using land, labor, and capital. Notice we denote land with an N. Assume we are initially at an unconstrained equilibrium. What happens if the farmer is forced to use less land in the production of wheat? Well, we make the same assumptions as we did a bit earlier. The disequilibrium now becomes that the value of marginal product land used in wheat divided by the input price of land is greater than the value of the marginal product of labor in wheat divided by the wage rate, if you like. And the reason for that is because we've got a constraint. And when you have a constraint, you're using less land in wheat. And because of our assumptions, the marginal product of land in wheat goes up because less land is used to produce wheat. But notice that the equilibrium remains in place for the other goods for now. So the value of the marginal product labor in wheat divided by the input price of labor is equal to the value of the marginal product K in wheat divided by the input price of capital, and it's equal to 1. This is the only inequality here. So what happens? Well, the farmer should use less labor and capital to produce wheat. So the farmer reduces the amounts of labor and capital used, which increases the marginal product of labor in wheat and capital in wheat, and thereby we get this becomes an equal sign, and everything is now equal except it's greater than 1. So now the question is, what happens on the barley side? Well, barley, nothing changes because there's no ability to influence the marginal product of labor, say, by changing the marginal product of wheat. Changing the marginal product of labor in wheat doesn't change the marginal product of labor in barley. So in barley, we get this equilibrium condition, so we have an unconstrained optimal condition. Now, suppose the farmer has excess land, then it must go somewhere. If the price of land, the rental rate on land is fixed, the farmer will rent out the land. If this is not the case, if it's not possible, the shadow price of land falls. So you've got extra land, and we know from linear programming that the shadow price of land is effectively 0. Therefore, in barley, the value of land in barley over R of n is greater than 1 because more land is used to bring down the marginal product of land in barley. So in other words, we take the land out of wheat and put it in barley. Assuming that the cross partial of the production function with respect to input-output is 0, then no further adjustments are made. But the questions remain. Is there excess labor so its shadow value is lower? And is it possible that there's excess capital on the farm? And what should be done with it? Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.